Hello friends, welcome to another lecture of electromagnetic theory for BSc and MSc students. Today we are going to discuss about Fresnel's equations of reflection and refraction. Okay, so before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHA LAKHYAJIT 123. This is my Insta ID, so you can follow me on Insta. So now let's start. Now let us consider two dielectric medium. Suppose one is this one is medium 1 and this is medium 1, and this is suppose medium 2. Okay, medium 1 and 2, and here you see characterized by the constants mu1 and epsilon 1, mu1 and epsilon 1. This represents permeability and permittivity, right? So here mu2 and epsilon 2, let me consider that way. And suppose let me take this is the normal, suppose. Okay, and let me use another color, and let us consider electromagnetic wave. Plane electromagnetic wave is incident obliquely on the plane boundary. Okay, so it incident on this sorry, just give me a second. So this is incident plane electromagnetic wave. Okay, and now, and this is the reflected wave, electromagnetic wave, and this one is the transmitted one. Okay, so let me consider that way. So here this is suppose x-axis, and this is suppose z, and here you see this is the angle of incidence, theta I, right? Theta I, and this is the angle of reflection, angle of reflection, and this is the angle of reflection. Let me write angle of reflection is theta R, and angle of reflection is suppose theta R dash, and which must be equal to, according to the laws of reflection, it must be equal to theta I, right? Theta I. And this is the incident electromagnetic wave. This is the incident EM wave, right? So, and this is the reflected EM wave, reflected EM wave, and this is the transmitted EM wave, right? Okay, now let me write what I have considered here. Okay, so let us suppose a plane electromagnetic wave is incident obliquely on the plane boundaries, separating two dielectric media 1 and 2, referred as medium 1 and 2, and characterized by these constants mu1 and epsilon 1, mu2 and epsilon 2, okay, respectively. And mu1 and mu2, so for two different media I have used media mu1 mu2, epsilon 1 epsilon 2. Mu represents permeability, and epsilon represents permittivity, right? I will mention those later. Okay, so these are the symbols that we're going to use. K is the propagation vector. For different vectors I'm going to use different symbols, like k1 this k. Let me write here. Propagation vector of this wave is k1 vector, and this one is suppose k1 dash, the reflected one, and the transmitted or refracted, the propagation vector of this vector, reflected vector, is suppose k2. Okay, let me write that way. Okay, then now you see So the field vectors of incident, refracted and refracted wave are given by this equation. First one is given by equation, first one incident wave is given by the first equation, and refracted wave is given by the second equation, and the reflected one will be written on the other side. Okay, so this is propagation constant associated with this wave is k1, and this is k2, sorry, not k2, k1 dash, that's supposed to be k1 dash, and this is k2, right, k2. Okay, and the refracted or transmitted wave, this is given by this equation number 3, right? So here we're going to get two cases. First one, so let me write case 1. Here the E vector is perpendicular to the plane of incidence. E vector is perpendicular to the plane of incidence. Sorry. So the plane of incidence means the plane which contain all the three rays. That means now you see this is the incident wave, and this is the boundary where it strikes, and this is the normal, suppose, and this is the transmitted, and this is the reflected. The plane on which these three wave lie, so that's going to be the plane of incidence. Don't think that the boundary is the plane of incidence. Okay, so this incident ray strikes on this boundary. It doesn't mean that boundary is the plane of incidence. Plane of incidence means the plane contains both reflected and incident wave. Okay, and now you see here, so if this is the wave, electromagnetic wave, that means we have considered this E is perpendicular to the plane. That means this E is either direction of E is either into the page or into the screen of your device where you are watching this video, or it is coming out of this device. Okay, and then in that case magnetic field will be in this direction, right? That means this is the case. If this is the direction of propagation of the wave, if this represents the magnetic field, then this is going to represent the electric field, direction of electric field. Both are mutually perpendicular to each other. And if this is the plane, here you can see, then this is electric field we are taking. It is coming out of the page, perpendicularly, normal to the page, or it is going into the page. Okay, that means the electric field gonna vibrate this way, in this direction. Okay, and the magnetic field will vibrate in this way. Okay, and the wave will be propagating in this direction, right? So hope you have understood this. So that is the case. Now let me clean this. Okay, now you see, since the electric field vectors are parallel to the boundary surface, right? Electric field vectors are parallel to the boundary surface. Okay, electric fields are perpendicular to the this plane of incidence, but they are parallel to this boundary. Okay, that's where. So what are we going to write here? And we know that tangential components of electric field vectors, E at the interface requires we can write that way, that since electric field vectors, or we can simply write this E vector, okay, let me write here electric field vectors. Electric field vectors, that means E1, E1 dash and E2, okay, are parallel to the boundary surface. the continuity of the tangential components of electric field, the continuity of the tangential component of the field vectors that means I'm talking about E vector, okay, at the interface that means at the boundary requires that E01 plus E01 dash is equal to E02. Okay, now you see, in case of magnetic field vectors, B vector or H vectors, here you can see, if you see the diagram, now you see, let me explain here. This is the boundary, suppose, where the electromagnetic wave strikes, and this is the normal. Here you see this is the incident wave, and this is the angle of incidence theta I, and the magnetic field is in this direction. We have taken this B vector, and the electric field is this perpendicular to the screen of your device, okay, which is already parallel to this boundary, if you imagine that way, right? This is so now you see, now tangential components of B, that means here you see this boundary, this boundary is not just a line, it is a plane like this, okay. So in that case, this vector, this E vector, which is perpendicular to the device, that's going to be this vector, this E vector, which is perpendicular to this device, screen of this device where you are watching. For that vector, this boundary plane is parallel, okay, think that way. So now you see, now if we consider the magnetic field which is perpendicular to here, it is oscillating in this way, and which here you see it must have two components. One is perpendicular to this plane of this boundary, the interface, and parallel to the interface, that will be the tangential component. Now if this angle is theta 1, this angle will be also theta 1. Let me explain how. Because you see, this is 90 degree as this is normal, okay, so that's why this angle must be 90 minus theta 1, right? This angle must be 90 minus theta 1, because this is theta 1, so it must be 90 minus theta 1. If this is 90 minus theta 1, then sorry, I have taken theta I, okay, so then you see, here you can see this angle is theta I, then this is alternate interior angles, this must be also theta I, and this B is perpendicular to this wave, so that's why this angle, here you can see this angle, this one, this must be also 90 minus theta I. If this is 90 minus theta I, that's why it must be theta I, then these two components will be perpendicular, right? So hope you have understood this. So if you have not understood, let me explain it again. Now you see, this is the normal and this is the interface boundary, okay, and here is the angle of incidence theta I. Who have understood this, they can skip this part, okay, few seconds, okay. So those who have not understood, let me explain again. This is the magnetic field which is perpendicular to this one, so it must have two components. One is perpendicular to this boundary in this direction, okay, and one is parallel to this boundary in this direction, okay. This is the magnetic field vector B. So now you see, if this is theta 1, this is also theta 1, alternate interior angles, theta I, not theta 1, and this is normal, so this must be 90. This is normal, right? This must be 90. If that is the 90, then it must be 90 minus theta I. If this is 90 minus theta I, right? Now you can see, if this is theta I and this is that must be 90 minus theta I, because this vector is perpendicular to this wave, right? So this must be 90 minus theta I, right? So if this is 90 minus theta I, again you see these two are perpendicular. So if this angle is 90 minus theta I, that must be theta I, right? Hope you have understood. So that's why tangential component of this B vector is B cos theta. This is the tangential component. Similarly for this one, so here we're gonna get tangential components in this direction, right? In this direction, this is the perpendicular component, and here we're gonna get B1 dash cos theta. Similarly for the transmitted wave also, we're gonna get like this B2 cos theta. Here we're gonna get cos theta r, as we have taken this is theta r, right? And here we're gonna get theta r, this angle of reflection is equal to angle of incidence, so here we can write theta I. So hope you have understood this, right? So now you see these two are in positive direction, this is pointed in the negative direction, right? And this vector is either you can write B or you can write H also. So we're gonna use here H, okay, or you can use H here, okay. So now let me clean these things. So the hope you know the relation between H and B, right? B is nothing but mu H. I hope you know these things, okay. So now you see, similarly, so let me take this as equation number suppose 4. Similarly the continuity of the tangential components of the magnetic field at the interface requires that H01, here we're gonna write negative for the first incident one, which was directed in the negative direction, as I have already explained, then plus H-01 for the reflected wave cos theta r dash, which also can be replaced by cos theta I, because theta I and theta r dash are equal, angle of incidence and angle of reflection are equal. Then here we're gonna get minus sorry, just give me a second. Okay, just so this was the incident. Here we have got two components of this magnetic field vector, this is H, and here this way we have got this one, this is positive direction, this is negative direction. Here we will take the magnetic field in this direction, then here this is gonna be the perpendicular and this is gonna be the tangential. Here again this is gonna be negative, okay, not positive, negative, okay. Two components we're gonna get negative, right? So then what we have to write here, minus H02 cos theta r, and so this implies that H01, if you simplify this, then H dash 01, you can take this cos theta I common, then H02, then cos theta R. That's what you can write. Okay, let it be equation number 5. Suppose this is equation number 5. Now let me go to a new slide. Okay, and let me mention one more thing, that angle of incidence, that is theta I, is equal to angle of reflection theta R dash, angle of reflection. Okay, so in the next page here, we know that from this equation, you can see from this equation what we can write. From equation number 1, what we can write, that B1 vector, that is equal to K1 cross E1 divided by omega 1, and B1 gonna be mu1 H1, right? So that's why it implies H1 vector is equal to K1 cross E1 divided by mu1 epsilon 1. That's what we can write. Okay, since, let me mention here, since B1 vector is equal to mu1 H1, right? That's what we can write. So now you see let me mention one more thing. Just let me go back. Here you see in equation 1, 2 and 3, though I have written mu1, mu2, mu3, mu1, mu1 dash, and here you see, here this is mu1, and here I should write mu1 dash. Okay, sorry, not mu1, omega 1 frequency, this omega 1 dash, and here I should consider omega 2, but here remember that omega 1 dash and omega 2, both all the three frequencies are equal, and here let me consider all the three be, each of them be omega. So, okay, let me mention this one. Okay, so if that is the case, here you see okay, now you see, if we consider that n1 cap is the unit vector along k1 vector, then what we can write? We can write this this way: k1 n1 cap cross E1 vector, and here mu1 omega 1. And remember one more thing, that k1 is equal to omega 1 by, this is b1, right, which is the speed of the wave. And if that is the case, and speed of the wave is given by root over mu1 omega 1. Okay, and that's why we can write here, you see, speed of the wave is actually given by 1 by root over mu1 omega 1, and that will that will give you omega 1 into root over mu1 omega 1. That's what we're gonna have. Okay, so if we use these values, then this h1 gonna be equal to, so we're gonna replace this k1, okay, by this value, and then this omega 1 will cancel this omega 1 if you replace this k1 by this value, right? Then this root omega 1 cancel omega 1, mu 1 to give root mu 1. Then it's gonna be equal to, you know, first let me put the value here. Okay, root over mu1 omega 1 by mu1. Okay, this omega and this one cancels, right? That means here we have omega 1, here we have omega 1, these two cancel, right? These two are cancelled, and n1 cross E vector, that's what we have got. So from this equation, now you see this v, that speed of the wave, is given by 1 by root over mu1 epsilon 1, and that gives you this omega 1 root over mu1 epsilon 1. And if you replace this k1 by this value of k1, then what you're gonna have, then here you should get epsilon 1, here you should have omega 1, this one omega 1, then omega 1 cancels, right? That's what you're gonna have. So this gives you root over epsilon 1 by mu 1 n1 cap cross e1 vector. So therefore we can write the amplitude that h01, that's going to be equal to root over epsilon 1 by mu 1, and then here we're going to take again the amplitude of E vector, that is E01. So similarly we get H01 dash, here we're going to get root over the reflected and then the incident and reflected are in the same medium. Here you can see these two waves are in same medium. For the same medium we get this mu1 and epsilon 1 same, right? So here also we're gonna get mu1 epsilon 1 root over epsilon 1 by mu1. Here we have got E01 dash, that's what we're gonna have. And for the transmitted wave or reflected wave, refracted wave, what we're gonna get, that H02, that's gonna be equal to root over, here we're gonna write epsilon 2 for the other medium, medium 2, right? Mu 2 and E02, that's what we're gonna have. So now let me take this as equation number. Now what was the last equation we had taken? So last number is equation number 5. So here let me take this as equation number 6. Okay, now let us use this results in this equation number 3 in the equation number 5. In this equation, in equation 5, let us use 6 in 5. Okay, so using 6 in 5, what we're gonna have? Okay, so let me write here. Sorry, just wait, give me a second. Okay, so using equation number 6 in 5, so this was equation number 5. Here we're going to use the equation number 6. Okay, using 6 in 5, what we're going to have, root over epsilon 1 by mu 1. Okay, epsilon 1 by mu 1, within bracket, after taking common, we're gonna get E01 minus E01 dash, and cos theta I is equal to, on the other side, epsilon 2 mu 2 into cos 02 cos theta, E02 cos theta R, right? That's what we're gonna have. Now let us eliminate this E02 from this equation 4 and 5. From this equation number 4, let us eliminate this one 4, and from the equation not 2, 2 should not be written here. Okay, just let me do one thing here. Just do one thing, just replace this one by this result. Okay, so then what we're gonna have? Okay, so if we use the equation number 4 here, okay, then the left hand side remains same. This is the left hand side. Here we're gonna get this left hand side, and on the right hand side we're gonna have, sorry, root over epsilon 2 by mu 2. So instead of E02, what we're gonna write, we're gonna use this equation number 1. We're gonna write this E101 dash. So let me copy this. Okay, so here within bracket we're gonna write this. So this is obtained from equation number 1. Then cos theta r, that's what we have got. So here we're gonna write using equation number not 1, equation number 4. This is equation number 4. So we have used equation number 4 here. Now what we need to do here, okay, so we're gonna find the ratio of the amplitude of reflected and incident wave. So that's gonna be the Fresnel's equation of reflection, right? So let me copy this last equation and let me take a new slide. Okay, so here you see this is the last equation we have got. Okay, and here you see, if you open the brackets and multiplication, after doing multiplication and all the steps that takes to simplify this, after simplification, if we find the ratio of E01 dash by E01, then you're gonna get root over epsilon 1 by mu 1 cos theta 1, sorry, not theta 1, theta I, minus root over epsilon 2 by mu 2 cos theta r divided by root over epsilon 1 by mu 1 cos theta I plus epsilon 2 then mu 2, that cos theta r. Okay, so how we have obtained this? This is very simple. If you multiply this one with this one and this one, similarly this one with this one, then simplify. Okay, then what you gonna get? Root over epsilon 1 by mu 1 cos, sorry, not cos, here 0 1, okay, cos theta I, then minus root over u epsilon 1 mu 1, then E01 dash, then cos theta I, that's going to be equal to epsilon 2 mu 2 E01 plus root over sorry, I forgot the cos theta r, then plus root over epsilon 2 mu 2, then E01 dash, then cos theta r. Okay, that's how we simplify. Then you see, then what we have done now, now you can see that clearly what we can do here. Okay, so this one and this term, if you bring this one to this side, then what you're gonna have, you're gonna have this root over u epsilon 1 mu 1 is taken common, suppose, then within bracket you're gonna have cos, within bracket you're gonna have cos theta I minus cos theta r, then this E01 is taken common. Similarly, if you transfer to the other side of this equal sign, then that's going to be positive, and you can take these two common, sorry, not these two, sorry, okay, this two, this term which is under root, that not going to be common here. The common part is only the amplitude, that E01. So here we're going to have again root epsilon 2 and mu 2, right? Because here we have epsilon 2 and mu 2, right? So So hope you have understood. When it is transferred to this side, so this positive sign becomes negative, right? And similarly this one to other side, you can take common E01 dash. This E01 dash is common here and nothing else. Then again you can write root over epsilon 2 by mu 2, then cos theta I plus then root over, then that means you can get this part here. Okay, then from these two you can obtain this ratio, right? So if you get here root over epsilon 1 by mu 1, not epsilon 1, it's supposed to be epsilon 1 and mu 1, and it's supposed to be epsilon 2 mu 2, and here we supposed to get, here we should get cos theta r, right? So that's what we're gonna have now. So from here, if you find this one by this one, then this one should be divided by this one. Okay, so that's what we're gonna have. Then we're gonna get this result, right? So hope you can do this simplification by yourself. This is very simple, right? Sorry for this disturbance. Okay, now let me clean this page. Okay, now you see what we can do here. So let me use the symbol, perpendicular symbol. This denotes the that electric field is perpendicular to the plane of incidence. Okay, so hope you have understood this, right? So let me take this as equation number 7, and here you see this is the ratio of amplitudes of electric field vectors in incident and reflected wave. Okay, this is one of the Fresnel's equation. Similarly, what we can do, right? Let me go back to the previous slide. Here you can see, instead of replacing this E02, if we replace E01 dash, okay, if we replace E01 dash using this equation, equation number 4, then E01 dash, that's going to be equal to E02 minus E01. Okay, and if we use this one here in this equation, then this is gonna give you just give me a second. Okay, now just 1 minute. Okay, wait, just do one thing. Let me give it equation number 8, and let me give this one equation number 8, and let me take this as equation number 7. Okay, now using 1 in 7 again, let me copy this equation number 7. Okay, just give me a second. Just here, this is the equation number 7. Let me copy this one. Okay, so here is the equation. Okay, this is equation number 7, and in this equation let us use equation number 5. Okay, let us use this equation. Let me go back to the previous slide. Okay, so this equation, equation number 4, let me use this equation. So from here we get the value of E01 dash. Okay, so if we, let me copy this. Okay, so let me use this value. Okay, let us put here. Okay, that was equation number 4. Okay, so then what we're gonna have, you see, just give me a second. If we replace this E01 dash by what, E02 minus E01, then because of this minus, this is gonna be plus, right? So hope you have understood this. So here what we're gonna write, using equation number 4, okay, so using equation number 4. So if we simplify this, that's gonna be again equal to here you see E02. After simplification we're gonna get I have written the result directly. I haven't shown all the steps here for the perpendicular components. Okay, so that's gonna give you 2 root over epsilon 1 by mu 1 cos theta. Cos theta is not under root, okay, this is outside the root, so divided by epsilon 1 by mu 1 into cos theta I plus root over epsilon 2 by mu 2 into cos theta r. That's what we're gonna have, right? And this is the ratio of amplitudes of electric field in incident and refracted wave, right? Incident and refracted wave, not reflected. Okay, here we can write ratio of amplitude of electric field vectors in incident and refracted waves, right? So let us take this is equation number 9. This is equation number 9. Suppose just give me a second to adjust this. Okay, this is suppose equation number 9. Let me take this is equation number 9. And let me tell you one more thing, that here you can see this is n1 cap e1 cross product of n1 and e cross 1. It is nothing but n1 e1 sine 90, right? Because e1 is perpendicular to the direction of the propagation of the wave, and this n1 cap is the unit vector along this k1, right? So angle between them is 90, right? So hope you have understood this. So sine 90 is 1. And now you see these two equations, as we have considered both a dielectric medium, then we can write these two equations in another form, that is you see. So let me take the new page. Okay, now you see in case of dielectric medium, or you can say non-conducting medium, that mu1 and mu2 both are equal, and here we have taken the permeability of both medium are equal, and let's suppose both equal to mu naught. Okay, where mu1 and mu naught equal to mu1 and mu2 equal to mu naught. Okay, now refractive index of the medium 1, refractive index of medium 1, that is, let me suppose n1, and which is equal to actually relative permeability, that is mu1 by mu naught, that gives a relative permeability mu r. You can say, instead of writing mu r, I have written directly mu1 by mu naught, and relative permittivity epsilon 1 by epsilon naught. So that's gonna be equal to, since mu1 is equal to mu naught, if you put that, then that's gonna be equal to here root over epsilon 1 by epsilon naught. Similarly, refractive index of medium 2, that is n2, that gonna be given by epsilon 2 by epsilon naught for medium 2, right? So now you can see that n2 by n1, that ratio will be equal to, if you divide n2 by n1, then that's going to be equal to epsilon 2 by epsilon 1. That's what we have got. Now if that is the case, then the equation number, this equation here, you see equation number 8, what we can do here, we can replace these terms by, just do one thing. Okay, this mu1 can be replaced by mu naught, mu1 and mu2, right? Let me copy this equation number 8 and let me write this one in the new slide. Okay, so then just wait, give me a second. So therefore now you see equation number 8 implies this. Now let us replace mu1 by mu naught. So mu2 is also mu naught. So mu1, mu2, both these are mu naught. That's what we have got. Now you see what we can do in this case. We can multiply root over mu naught with the both numerator and denominator. Both numerator and denominator are multiplied by mu naught. Then what you gonna have, or you can take 1 by mu naught common from both numerator and denominator, and those two will be cancelled out. Or you can just do one thing, just give me a second. Instead of that, let's do one more thing. Let's multiply. So we are supposed to get root over epsilon naught by epsilon 1. So let's multiply mu naught, root over mu naught by epsilon 1 with the both numerator and denominator. Let's see what we get. Mu naught by epsilon 1. Then what we're gonna have, if we do so, then let me clean this. If we do so, then what we're gonna have? Then we're gonna have that cos theta I, that's gonna be equal to, minus epsilon 2 by epsilon naught. When you multiply with this one mu naught by epsilon 1, then this mu naught will be cancelled. So we're gonna end up getting this, right? So hope you have understood this. So here we're gonna get cos theta r. Similarly, in the denominator also we're gonna get here cos theta I plus root over epsilon 2 by epsilon naught. So cos theta r, that's what we have got, right? So now this is nothing but equal to n2 by n1. So we can replace this n2 by n1. Okay, so if we do so, then what we're gonna have here, then this e naught 1 dash by e naught 1, that's gonna be equal to cos theta I minus n2 by n1 cos theta r and cos theta I plus n2 by n1 cos theta r. Now we're going to use the Snell's law, right? So according to that, you see, using Snell's law, here we should get n2 by n1, that's going to be equal to sine theta I by sine theta r. So let us use this here. Then this let me copy this. So here is the result we're going to have. Cos theta I minus sine theta I by sine theta r into cos theta r divided by same result, but here the sign will be positive in the denominator. So here you see this is gonna be positive here. Okay, that's what we have got. Then again, if you simplify this, then if you multiply both the numerator and denominator by sine theta r, then you're gonna have sine theta r cos theta I minus sine theta I cos theta r divided by here in the denominator we're gonna get the same but with the positive sign. So here it's gonna be positive, and this implies so here you can use sine a cos b, cos a sine b, so sine a minus b, right? Similarly here we can apply sine a plus b, so that's why we have got e naught 1 dash by e naught. So here it becomes sine theta I minus sine theta minus theta r, and here sine theta I plus theta r. That's what we have got. Okay, this is what was the last equation number we have. Okay, equation number 9. So this is suppose equation number 10. Okay, now you see, so using those results, so what will be the simplified form of this equation number 9? So let me copy this equation number 9 and let me take a new slide. So this is the equation number 9, right? If we use these relations here, that n2 by n1 is equal to root over epsilon 2 by epsilon 1, which is again also n2 by n1 is also equal to sine theta I by sine theta r, right? If we use those relations here also, then this equation will give you 2 cos theta I sine theta r divided by sine theta I plus theta r, right? So last equation was equation number 10, so let it be equation number 11. Let me show you how. Okay, so here we can write using these relations. So now you see, here you can see this can be replaced by n1, right? And this can be replaced by n2. When you see, if we replace, just give me a second. So if we replace mu1 mu2 by mu naught, okay, as I have considered, let me replace this mu1 mu2 by mu naught. Okay, then this equation number 9, e naught 2 by e naught 1, that's gonna give you 2 here n1 cos theta r divided by n1 cos theta I plus n2 cos theta r, right? So then what we can have here, so if we divide both the numerator and denominator by n1, then we're going to have 2 cos theta I by cos theta I plus n2 by n1 cos theta r. Now if you replace this n2 by n1 by this value using Snell's law, then what you can have 2 cos theta I by cos theta I plus sin theta I by sin theta r cos theta r. That's what we're gonna have, right? So now you see, if we multiply both the numerator and denominator by sin theta r, this one and this one also, if we multiply both the numerator and denominator by sin theta r, then this sin theta r will be cancelled, right? Then what we're gonna have 2 cos theta I sin theta r, and here we're gonna have sin theta r cos theta I plus sine theta I cos theta r. Then here you see this is sine A cos B, sine B cos A, and this is 2 sine theta I sine theta r. So if we apply the sine A plus B formula, then we're gonna get this expression. So this is equation number 10. So here I have shown how we have got this expression. This is the simplification that I have shown here, right? So this is all about case 1. So equation number, here you see, equation number 10, and the equation number, so it's supposed to be 11, right? Sorry, let me make it 11, equation number 11. Equation number 11. So these two are the Fresnel's equation, right? Okay. So when you are asked to derive the Fresnel's equation of reflection, then you have to write this. Let me show you. For reflection, you need to divide this equation. Okay. Derive this equation. For reflection, Fresnel's equation of reflection. Here we have, this is the amplitude of the reflected wave, right? Hope you have understood this. Amplitude of the electric field vector of the reflected wave, and this is the incident, right? And for refraction, if you are asked to write the Fresnel's equation for derive the Fresnel's equation for refraction, then you need to derive this equation number 11 for refraction, in case of refraction. So this is all about case 1. Now case 2. So when this E vector is parallel to the plane of incidence, E vector is parallel to the plane of incidence, right? So now the diagram should be like this. Let me draw here. So this is the boundary separating the medium 1 and 2. This is 2 and this is medium 1, and here is the normal, suppose, and here is the normal, and let me draw the incident incident wave. So this is the incident wave, suppose. Just give me a second. This is the incident wave, and this is the reflected wave, and this is the refracted or transmitted wave, you can say. Okay, so this is the propagating constant, propagation vector, and this is k1 dash, and this is the propagation constant, propagation vector for the transmitted wave k2. So here you see, in this case, the electric field is parallel to this plane. This is the plane of incidence. Okay, this is the electric field. So associated with the incident wave is E1 here, and here E1 dash is the electric field associated with the reflected wave. This is E1 dash, and similarly electric field associated with this is E2 vector. Okay, so again now we have considered here you see here permeability and permittivity, mu1 epsilon 1, here mu2 epsilon 2, right? Okay, now you see what we can do here in this case. Now here you see magnetic field vector is now perpendicular to the incidence plane of incidence. Okay, in the previous case electric field electric field vector was perpendicular to the plane of incidence. Now electric field vector is parallel to the plane of incidence. Okay, magnetic field is perpendicular to the plane of incidence now. Okay, so here you see, so what we can do here now, here we're going to write that in this case the magnetic field vectors are parallel to the boundary surface. Boundary surface means this one, and the plane of incidence is perpendicular to the boundary surface. Okay, so parallel to the boundary surface. Right, so hence continuity of tangential components of let me write here. Continuity of tangential components let me write it of the H vector at the interface requires H01 plus H01 dash is equal to H02, right? And similarly tangential components, so similarly tangential components of E vector requires, now you see, as this H vector are already parallel to this interface, right? So that's why we don't need to resolve this in components, tangential and parallel components. So this vector and this H vector is itself tangential to this surface, but E vector is not tangential to this surface, so it must have two components. One is perpendicular component and tangential components. This is the perpendicular components which is perpendicular to this interface, and this is the tangential components, right? So this component, if here you see, if this is theta I and this is theta I, which is also equal to theta r dash, that means angle of reflection, which is also equal to angle of incidence, and this is the angle of refraction, right, theta r. Okay, so that's why now you see, let me write this E1 here. Okay, now you see this component will be, this is in negative direction, minus E1 cos, so this is theta I, cos theta I, and similarly here the tangential components is cos E1 dash cos theta r, so which can theta r dash, actually this is theta r dash, which can be replaced by theta I, right? And here tangential components, this one is in this direction, that is again negative E2 cos theta r minus E2 cos theta r, right? So that's why what we can write here, we can write E01 cos theta I minus what we have done here, right? So this is negative and this is positive, this one is positive, in positive direction, E01 dash cos theta I, theta r is replaced by theta I, theta r dash is replaced by this, theta r dash is replaced by theta I. Okay, then this one is again negative, minus E0 to cos theta r, right? So hope you have understood this. So now so this can be rearranged and simplified, and doing so, what we can write that E01 minus E01 dash, taking cos theta common and multiplying negative sign on both sides, then we're gonna get here positive 02 cos theta r2, cos theta r. That's what we're gonna have. So this is now here, you see. So what was the last equation number? We had taken 11. So let me take this as suppose 12, and this is suppose 13. Okay, 12 and 13. Now let me copy these two equations and let me go to a new slide. Okay, this is the 12. So here is the new slide. This is equation number 12, and 13 is this one. Just let me copy this equation and let me paste here. This is equation number 13. Okay, so these are the two equations that we have got now, right? So again, we're gonna use those relations that we have got here. You can see. Let me go back to the previous slides. Just wait. Now let me use this equation number 6. Okay, in equation number maybe 12, I think 12 or 11. So let me check equation. So equation number 12. Let me use equation number 6. Okay, this equations here in this equation number 12. Okay, then what we're gonna get? So now let me cut it. Just using equation number 6 in 12. So what we can write here? Root over epsilon 1 by mu 1 E01 plus root over epsilon 1 by mu 1 E01 dash. That's going to be equal to epsilon naught. Just wait. Actually, that's supposed to be epsilon 2 by mu 2 and E02, right? That's what we should get. Okay. So now you see here what we do in this case. Now if we replace this value from using this equation, so from this equation number 13 we're gonna get E0 to E02. That's gonna be equal to E01 minus E01 dash cos theta I divided by, we're gonna get cos theta r. So let us use this value here. Then what we're gonna get here, you see. Okay, so then this E02 will be replaced by this value from equation number 13. We're gonna use this value. Just give me a second. Okay, so here we have got this equation, right? Okay, so using equation number 13, right? So that's what we have done, right? So now what we're going to do here, here you can see we can take these two common, right? And if we do so, then what we can write this way, just within bracket, this one we have got. So that's what we have got, right? So now you see, if we simplify this and to get from here, if we want to obtain the ratio of the amplitudes of the reflected and incident wave. So here we have taken E is parallel to the plane of incidence, so that's why parallel symbol is given here. So then what we're gonna have, let me do one more thing. So for dielectric mediums, we have considered mu1, mu2 is equal to mu naught, right? So if we use that, then here we're gonna write mu naught, and this mu2 will be also equal to mu naught, right? So that's what we're gonna have. So if that is the case, then so what we can do here, just give me a second. So instead of writing the result directly, let me simplify this. Then this e naught will be cancelled, root over e naught will be cancelled. Then if that is the case, then we're gonna have e naught 1 plus e naught 1 dash is equal to root over epsilon 2 by epsilon 1, and here we're gonna have e naught 1 minus e naught 1 dash cos theta I by cos theta r. That's what we're gonna get here. Okay, so now you see, just give me a second. So in this case, what we can do is, now you see, if from these two terms, this one and this one, if you multiply, or if you open this bracket, then what you can get, and if you transfer this one into this one to the left side, then if you take the e naught 1 common, then you're gonna get u naught 1 within bracket. We're gonna have 1 plus, sorry, not plus, here we're gonna get minus 1 minus root over epsilon 2 by epsilon 1 cos theta I by cos theta r. Similarly, if you transfer this one to the right hand side, then taking e naught 1 dash common, then we're gonna have e naught 1 dash, that's gonna be equal to 1 minus just give me a second, wait, so not 1 minus, actually we can make it positive if we want. Yeah, just okay. So here it's gonna be, so if you take the minus sign common, then it can be plus, then root over epsilon 2 by epsilon 1, then here we're gonna have cos theta I by cos theta r, and that's what we're gonna have. So let me copy this equation, let me go to the new slide. Okay, so here is the last equation that we have got, and from here what we're gonna have, if we find this, then what we're gonna have, so if you make it positive, then this one will be negative, this one will be positive, right? So that's what we're gonna have. Okay, so now minus 1 plus root over epsilon 2 by epsilon 1 cos theta I by cos theta r divided by 1 plus root over epsilon 2 by epsilon 1 cos theta I by cos theta r, and then simplify this. If you multiply both the numerator and denominator by root over epsilon 1 cos theta r, or simply multiply both numerator and denominator by cos theta r, right? That's going to be epsilon 2 by epsilon 1 cos theta I, and here we're going to get cos theta r plus root over epsilon 2 by epsilon 1 cos theta I. That's what we're gonna have, right? Or what we can do, or we can simply write this way. Just give me a second, we can write this way. Okay, just give me a second. So we can write this way. Right, similarly This one also can be written this way. Okay. Now you see, we have already got that n2 by n1 is equal to root over epsilon 2 by epsilon 1, which is also equal to sine theta I by sine theta r. We have already used these relations. Okay, using these relations, okay, since using these relations, what we can write here, okay, so we can replace this by sine theta I by sine theta r, right? And similarly we can replace this by sine theta I by sine theta r, right? So then what we gonna have here, if you multiply both the numerator and denominator by sine theta r, then it gonna be equal to sine theta I cos theta I minus sine theta r cos theta r. Similarly, denominator will be same terms, but here it comes with positive sign. Just give me a second. Let me write this one here. Okay, so we're gonna get this, but here it will be positive, right? So here you see, okay, just a second, a little bit of adjustment. So here you can see this is cos theta, and this is equal to nothing but 10 theta I minus 10 theta I minus theta r divided by 10 theta I plus theta r. This is trigonometric identity, right? So hope you know this. So now you see what we have got is now E01 dash by E01. So here the parallel components is equal to 10 theta I minus theta r by 10 theta I plus theta r. Okay, so this is suppose equation number, what was the last equation number we have got? 13. Now it is suppose equation number 14. Okay, equation number 14. So this is you see amplitude, ratio of the amplitude of E vector associated with the reflected and incident wave. Okay, and for the reflected wave, what we can do here, you see, let me show you. Before that, let me write here. Okay, now this is also Fresnel's equation of reflection in dielectrics. Okay, for the second case, and now let's derive the Fresnel's equation of refraction. Now you see from this equation, let me go back. So from this equation, if we copy this equation, so let it be suppose capital A. Let me take this as capital A. In this equation, what we can do now, you see, if we replace this E001 dash from this equation, what we're gonna get? So from this equation, E001 will be E001 dash, that's gonna be equal to divided by cos theta I, and if you simplify this, then E001 okay, E001 cos theta I minus E002 cos theta r. That's what we're gonna have. Okay, so now what we gonna have here, so this also can be written this way. If you divide each term by this, then it also can be written in this way. Just give me a second, just wait. It also can be written this way. So E01 minus this one divided by cos theta 1. Okay, so let us use this value here. Okay, then using 13 in equation number A. Okay, using 13 in equation number A. In A, right? So then what we're gonna get, let me go back to that slide. So let me copy this equation A, okay, and let me paste here. Okay, now you see we are going to replace this E naught, this E naught by this value. Here you see, let me cut this. We're gonna replace this by this value. Here you see, we're gonna use this value. Let me copy this. Okay, so here we're gonna put this, right? That's what we have got. Okay, now again, if you simplify this and if you replace, if you use those relations again, mu1 mu2 is equal to mu naught, and n2 by n1 is equal to root over epsilon 2 by epsilon 1 is equal to sine theta I by sine theta r. If you use those set of equations, then this can imply so what we can do here, just let me do one more thing, just give me a second. Okay, here this mu1 will be replaced by mu naught, and this will be also replaced by mu naught, right? Mu naught. Okay, then okay, so here this will be also replaced by mu naught. Okay, so if we multiply both each and every term by root over mu naught by epsilon 1, then we're gonna get e naught 1 plus, then here e naught 1 minus e naught 2 into cos theta r by cos theta I is equal to, here it's gonna be epsilon 2 by epsilon 1 e naught 2. That's what we're gonna have. So if you shift this one to that side, then if you simplify, so here we're gonna get 2 e naught 1, and on the other side we're gonna have epsilon 2 by epsilon 1, then plus 1, here we're gonna have e naught 2 common, right? That's what we're gonna have. Now use these equations. Okay, so if we use those equations, here it will be just of this form, right? Sorry, I made a mistake, I think. Okay, so here it's supposed to be cos theta r by cos theta 1 I. Okay, so I forgot to write that. Okay, just let me write it again. Cos theta r by cos theta I. That's what we get. So from here, let us find e naught 2 by e naught 1. Okay, let me write this the previous slide, in the next slide. Okay, let me copy this, and here we have got this last equation, and the sets of equation we're going to use here. We're going to use this. Here you can see we're going to use this equation. Let me copy this. Okay, just give me a second. Let me copy this equation. Okay, we're going to use this. So using this, what we're going to get, that 2 e naught 1. So here we're going to get sine theta I by sine theta r plus cos theta r by cos theta I e naught 2. So this is going to give you e naught 2 by e naught 1. So we are taking the parallel components, right? So that's going to give you 2 divided by this just let me copy this and paste here. That's what we're gonna have. Okay, so now what to do here, let's multiply both the numerator and denominator, cos theta I and sin theta r. Then here we're gonna get cos theta I. So let me write here properly. So then we're gonna have 2 into cos theta I sin theta r, and divided by, so this sin theta r will be cancelled. Then we're gonna have sin theta I into cos theta I. Similarly here we're gonna have, just give me a second, what we're gonna get here, this cos theta I will be cancelled. Okay, so here we're gonna get sin theta r by into cos theta r. That's what we're gonna have. So this implies, so let me write this one on the other side, or in the next screen. Let me take a new slide. Okay, so here you see, that's what we have got. So this implies, so here is the final result, 2 cos theta sin theta r. So here it's gonna be, just now you see we can write this like this way, taking half here and 2 into this and 2 into this. So we know that 2 sin theta cos theta is equal to sin twice theta. So if we apply that identity, then what we're gonna get here, we're gonna get sin 2 theta I plus sin 2 theta r, and this is nothing but, if we use the trigonometric identity, we have this is equal to nothing but sin theta 1 plus theta r into cos theta I minus theta r. This 2 gives this result. This is nothing but trigonometric identity. Okay, so remember that. So now let me take, this is what was the last equation we have taken, 14. Here you see, let me take this is equation number 15. Let me say this is equation number 15. Okay, so this is equation number 15. Just do it. Okay, this is the ratio of amplitudes of refracted and incident waves. So E02 and E01. Okay, now you see, so let me write the equations in single slide. Okay, for case 1, in case 1, what are the equations we have got when this vector is this vector was perpendicular to the plane of incidence, right? So what are the equations? So these are the equations 10 and 11 for the first case. Okay, when E vector is parallel to the plane of incidence, so what are the equations we have got? So these are the equations here, equation number 10, 11, equation number 14 and equation number 15 are Fresnel's equations of reflection and refraction of EM wave for dielectric medium or non-conducting medium, right? So when you are asked to find the Fresnel's equations of reflections only, then in case of reflection you have to take just give me a second what I have done here. So this for reflection it's supposed to be, you know, E01. Okay, so for refraction it's supposed to be E02. Okay, so this is the correction. So this is the amplitude of refracted and this is the incident wave, and this is the reflected wave and amplitude of incident. So here also similarly this is the amplitude of reflected wave, and here it's supposed to be E01 dash. Okay, and similarly you see this is the amplitude of, you know, refracted, that means the transmitted wave. Okay, so here you see these two equations, so equation number 10 and 11 for the first case when E is perpendicular to the plane of incidence, and these two equations of reflection and refraction for this case when E is parallel to the plane of incidence, right? So hope you have understood this well. So if you are asked to find the, you know, Fresnel's equation for reflections only, then you have to derive 10 and 14 only. If depending on the marks what is given, you have to take only one. Condition is not mentioned, case 1 or case 2, then you can do any one of them. If you are asked to find you derive both the reflection and refraction, you have to derive both 10 and 11. Okay, so thank you for watching. See you in the next video.